And hello, welcome everyone to this continuation on our discussion of the kOmega model in this turbulence modeling series. In the last video, when we were comparing some turbulent viscosity models in the website from CFD Online. So this is a standard K-epsilon model, and this is the kOmega model. So in the CFD Online website, we have nu t equals to k over omega. In here, it says that mu t, this one's the dynamic viscosity, equals to rho c mu k squared over epsilon. So we found that they are the same, what do you call that, expression, so long as this beta star here is 9 over 100, because that makes beta star c mu. Okay, so this makes beta star c mu. Alright, so I'll just do a equal sign here, c mu k squared divided by epsilon. Okay, so that is that. Maybe I'll just do this for that. Yeah. So next thing we'll want to compare the k equations between both of them, between the kOmega model and the k-epsilon model, just to get some understanding. So we kind of are familiar with the k-epsilon model, so we can start from here first. So what I did is I copied and pasted this equation, or I typed it out in Word, and this is what we get. Okay, so this is not exactly what we have from this one, the CFD online website. This one is what I've gotten from a textbook. So this is another form of an expression of the k equation for the k-epsilon model. Alright, so and then I want to compare between this and this, because they look a little different, especially this part as well as this part. Okay, over here, well, you can see that you just divide throughout by density, you more or less get this side. So let's do it step by step first. So pk is the production term, where you have this rate of strain tensor times the turbulent viscosity. This is actually common through both of them. Okay, these two p rates are pretty much the same, except for it being divided through by density. This is the buoyancy term that it's usually found in natural convection. We ignore it for now for the sake of simplicity. And the destruction term here, this d, is actually epsilon, because you divide throughout by rho, it becomes epsilon. This is the destruction term, the sink term, where turbulent kinetic energy is being drained. So the epsilon is actually the rate of dissipation of turbulent kinetic energy. So that's the other transport equation in the k-epsilon model. Ym here, I'm not really sure what that is, because this website doesn't really seem to give much information, and that's a little, well, a bit of a bummer, but we'll live with that for now. Okay, we'll live with that for now, and we'll just ignore it, because again, in most textbooks you won't see this many terms. Okay, SK stands for the source term. Source term meaning any kind of a source of turbulent kinetic energy that doesn't come from the production of K, from the stress terms, from the rate of strain terms, the rate of strain tensors. This is the standard way where mean velocity. Okay, let's get pinned. When mean velocity, the u bar, okay, sometimes it will dissipate and it will become turbulent kinetic energy, right? TKE, or maybe I'll just use KET, turbulent kinetic energy, which is equals to half u prime square ui prime square. There we go. Okay, so remember this is summed over x, y, and z directions. I'm using Einstein notation here, so it's shorter. Okay, summation. Sum it over the x, y, and z direction and you'll get that. And yeah, that is the K equation. So what I do is that I will divide throughout this to try and make this equation look more like this. This one I got it from the CFD, one of the standard CFD textbooks. There are several other forms as well you might see online. Okay, this is from CFD, A Practical Approach, this book. And sometimes you may find other expressions in this one called turbulent flow, and you may see an equation like this, where you have the you have it written in a very short form, where you have the total differential of K over time. So that is the time derivative plus the convection term. Then you have this second term, which is the turbulent diffusion term, which you see in this middle one. Then you see the production and the destruction term. So that is sometimes you see this D, you just write epsilon straight. Okay, so I just divide this throughout by density. So the next part is over here. I just divided everything throughout by density, and I got rid of this, and this, because they are kind of, I just ignore them. So first thing first, assuming a constant density, I just have my first term become like this. My second term becomes like this because I just got the density out. Okay. My third term, this is the viscous diffusion term of the turbulence kinetic energy. Alright, the viscous dissipation term of turbulence kinetic energy. I just divided the dynamic viscosity by density and became the kinematic viscosity. So it becomes nu here and nu t here. Okay. Then we'll have our production term here, pk over rho, which will be equals to this production term. So it depends how you define it, but this is how you define it here. And then, I mean, it's easy to see this pk here over rho will be equals to this production term, depending on how you find the equation. So D is the epsilon term, which is easy enough. So now it's just to compare these terms, okay, to the equation we have above. Alright, so a few notes of interest. First thing, you have this convection term. This one is pretty standard. Del by del x of k into ui. If you expand the Einstein notation out, it should be this. But of course, there are actually three terms at the back, right? So there was an intermediate step here. Alright, there's an intermediate step here. Equals to k plus ui partial by partial xi of k. Alright, so as you can see, this term here from continuity equation, partial ui partial xi equals to 0. Okay, so that's fine. So this term kind of disappears, and all you're left with is this term. Okay, so if you are incompressible fluid, we have this assumption. So we are left with this. That's why when you expand it out, you have this x, y, and z kind of direction if you're using Cartesian coordinates. The next term we kind of have to clean up is this term. So so you see this one. This is the diffusion term of turbulent kinetic energy. However, if you see this equation form, you only see the turbulent kinetic energy, turbulence diffusion term here, or this turbulent viscosity term here, divided by sigma of k. Then you have the x, y, and z. Okay, so this is the form for the what you will see in the textbooks, some of the theoretical textbooks. Even if you take a look at Wikipedia, the Wikipedia version of the K-epsilon turbulence model, they won't seem to have this dynamic viscosity here. I mean the normal dynamic viscosity, that is not the turbulence one, and it can be quite a bit of confusion, but don't worry, we're going to sort that out very shortly. Alright, so okay, so I'm gonna show you some papers in a bit, but the long and short of it, okay, so I'm just equating these two terms, alright? So normally there will be this viscosity term here, and then there will be this turbulent viscosity term. So these are kinematic viscosity, but why has it been truncated like that? Okay, so the reason why we do that is, okay, in the turbulence regime, this turbulence viscosity term is usually much greater than the kinematic viscosity of the fluid, so that you can just approximate, you can just neglect this term. Yeah, you can just neglect this term. I cite this Scott, this Dr. Scott. I think he did this for his PhD dissertation. Okay, so yeah, I'll run you through that very quickly. So yeah, this is it, and what he wrote there. What he wrote there is this. So this viscous term you see here, this one, the one I'm highlighting, that's corresponding to this kinematic viscosity, it is actually represented by this term over here, tau ijui. It says, since this represents the viscous transfer of turbulent energy, a very small quantity in contrast to the terms responsible for turbulent transfer in turbulent energy, it is neglected. So for most textbooks, you might see that it is neglected, like say this textbook, or in the Wikipedia page, or let's say even in this dissertation. Okay, but in CFD code, for example, inside this one, where you see this CFD online, or if you hop on to OpenFOAM, okay, so this is the K-epsilon model guide for OpenFOAM. If you hop on over to the source code, okay, the source code is here, you will see that they will use a term called the diffusion term for K effective, and then they will sum up nu T over sigma K, which is what we have here, nu T over sigma K. So this is how it's written in the OpenFOAM code, and then they will add on to this nu, which is the fluid kinematic viscosity here. So in most CFD codes, you'll find them, they kind of do this, they kind of do this summation. And if you want to take a look more at the code, it's over here. This is where the equation is. Alpha is just a term for, well, alpha is actually just a term for what do you call it? Multi-phase calculations. So you can just ignore that. So you see d by dt of rho times k. Then you have the Laplacian, the divergence of k. Okay, minus the Laplacian. So yeah, plus the divergence of k minus the Laplacian of rho times dk effective times k. This is like a multiplication kind of thing. So rho, which is the density, dk effective, which I just shown you just now in this C file. What it is nu T over sigma k plus nu, and then you multiply that into k. Alright, so that will be equals to the source terms and everything else. But what I'm saying is that, yeah, in CFD code, you don't ignore that. Why is that the case? Well, let me show you. Okay, I mean, in CFD, we don't ignore it, because when you try to simulate, let's say for example a boundary layer flow, or you have some fluid here going through a duct or pipe or whatever, when you go through here, you will have boundary layers over here, right? You have boundary layers over here, where in this regime, it really is true that nu t over sigma k is much greater than nu. Sure. So actually, that equation for k epsilon is pretty valid. I mean, the Wikipedia version or the truncated version, it is pretty accurate. Yep. Where we take this thing out, it's pretty accurate when it comes to this bulk flow, right? This bulk flow region. So the bulk flow region, this is accurate. However, when you come to the viscous sublayer, or the what do you call that? The boundary layer region, very close to the wall. All right. So if you have a velocity profile, it should be something like that. I'm not drawing it too right, but you get the main idea. Yeah. So in the viscous sublayer near the wall, normally we either use the log law of the wall, or there will be, we use the log law of the wall, but this transport equation, the transport equation, wait, no, this is not the viscous sublayer. It's just called the boundary layer, okay? The boundary layer is actually the viscous sublayer plus the turbulent sublayer plus the intermediate regime. So in this boundary layer, in the boundary layer nearer to the wall, you cannot say that nu t over sigma k is much greater than nu. So in fact, nu may be actually comparable to nu t over sigma k. Alright, so what do we do then? Do we have to, like, change the equation every time we switch from here to here? I mean, for practical purposes, no. So that's why in CFD code we tend to want to just keep this here and we don't neglect it, so that we can use one equation to solve in the bulk region and also in the boundary layer region. Of course, we adjust the boundary conditions using the log law of the wall, but that is the basic idea behind it. And yeah, if you want to know more, do check out this guy's PhD dissertation. It tells you how to derive this k equation so that there's less confusion. All right, so but I don't want to. Okay, maybe I'll do it. All right, so I won't go too much into detail, but you have your Navier-Stokes equation. Okay, you have your Navier-Stokes step 1. We have our Navier-Stokes equation. Step 2 is to okay, let's see. It's over here. Yeah, here. So we have our Navier-Stokes equation multiplied by the u. Okay, multiply Navier-Stokes by ui. So meaning to say, if it's in the x direction, you multiply by the x velocity. If it's in y direction, you multiply by the y velocity. And the z direction, you multiply by the z velocity, or w. Yeah. So you multiply by ui and then do your averaging. Okay. Then you what the next one is? All right. Where's this equation r? R is, let me check where r is. Oh, yeah, there's a lot of r's in this one. Okay. Oh yes, r is over here. That means it's the averaged Navier-Stokes equations. So okay. So derive k equation. So average Navier-Stokes equation, multiply by U bar I. So okay, so we have our Navier-Stokes equations, our general one. We multiply it by UI and we do averaging. Then the second one is to average our Navier-Stokes equation first, and then we multiply it by UI bar. So this will give you one set of equations, and this will give you the second set of equations. Then to derive K, subtract 2 from 1. So this is the general principle. Of course, multiply by half to get turbulent KE. Alright, so this is how the K equation comes about. Alright, so hopefully that clears up a lot of the confusion. I think I'll just put the link here. Okay. Yeah, I'll put some of these links inside the description, so you won't get too lost. So this is what we get for the K-epsilon equation, right? This is the one. And if you take a look at this one, this equation here. Okay, so we have this one here, all right, from the kOmega equation. All right. Yeah, so we have our K equation here. And for the K equation in the epsilon part, not the epsilon part, the turbulent kinetic energy part, if we look in the K equation for kOmega part, so this is from this website, so we just write down partial K partial T plus U J partial K partial xj. So this is an Einstein notation again, equals to tau ij. So this looks a bit different again, but not to worry. Partial K partial xj, okay, minus beta star kOmega. All right, and we plus partial by partial xj. Okay, then okay, I'm just gonna copy and paste because this is pretty much the same, right? Not gonna waste time. All right, so again we can compare term by term. What's the physical meaning of this? So this is the K from the K-epsilon model. So we can see immediately there's some resemblance. This one is equals to this. This one is equals to this because yeah. Okay, I'll just put this here. I'll copy and paste this over. Make it more familiar looking. This one is equals to this. Yeah, I think I should use the term J instead of I here to make it more consistent. Alright, so and this one is equals to this, which is fine. This one, beta K omega, at the bottom here, this term is actually just epsilon. So beta star K omega. All right. Yeah. In this weird formulation, this really weird formulation, yeah, omega is determined like this. I don't know why they have to do it like that, but yeah, this is the epsilon. This is the omega, and I should say omega star rather than omega. Not to confuse you, because this is the omega from the textbook definition. This is from the website, so I'll just use omega star to be consistent. Okay, omega star. because that's not the same omega that we are used to. Alright. Okay, so now that's a scaled omega, and yeah, we see that it is pretty much the same. So okay, only thing is that this tau ij d delta k delta xj, this is actually the production term here. If you can just do the comparison straight, right? Equals to tau ij delta k delta partial k partial j, and if you just compare this one's the rate of strain tensor thingy. You compare it to this, you will see a lot of the rate of strains over here as well. Whereas del uj del xi, so ui uj prime, this one is actually the tau ij equals to, this is the Reynolds stress term, so bar ui uj ui prime uj prime. Okay, this is the Reynolds stress term, if I'm not wrong. And then there's something else to it, right? Okay, dot dot dot. Okay, there's something else to it, but that's where it basically comes from. These are the closure terms. Alright. Yeah, and I don't want to write out the full expression, but just so you know, these two are pretty much the same. They have the same significance, and they produce K, turbulent kinetic energy. So if you take a look at the K-epsilon model and the kOmega model, the K equations are pretty much the same. There's no change to them. The form of which you write it may differ from time to time, but yeah, this is what it is. Yeah, and that is pretty much it. Okay, that's pretty much it. I'm not going to elaborate too much. In the next video, then we will try to tackle the similarity or the differences in the omega equation. Alright, so that's the more interesting bit. Alright, so yeah, thanks for watching. I'll see you guys again. Bye bye.